name is Olivia Wood. I'm the lead of the social media team and also the Mountain Spirit program, and I'm going to be your host for today for Deneb's rocket launch. First of all, let's start off with what is the RDL. So the RDL is an undergraduate rocket club at Embry-Riddle Aeronautical University. We are completely student-ran, and we are also performing liquid flight today. This will be a record-breaking for us and also record-breaking for any undergraduate liquid rocketry. It'll be, I'm pretty sure, the first undergraduate liquid flight vehicle to launch. And that's why we're here. We're here to watch Deneb today. Deneb is Block 2 of the Mountain Spirit program. And the Mountain Spirit program has the overall goal of reaching the Kármán line with a liquid flight vehicle. And what is Deneb? Let's give you some background information on Deneb itself. Deneb is a capstone project led by Cygnus Suborbitals. You'll hear more about them as the day goes on. We've been keeping up to date on them throughout the past few months. They started design and building their rocket last semester, and they finished building it this semester, and we are now at FAR for the second time for their launch attempt number 2. Deneb is going to be projected to go around 90,000 feet. It was originally expected to go around 150,000, but some constraints have restricted it to 90,000, and it also is going to produce 1,700 pound force. So if you guys have any questions about anything that's happening, you can drop them in the chat, and I will keep my...
Not the red team, not the red team, not the red team.
That's loud. Okay, I'll be keeping in the chat to keep up on your all questions. And now we're going to introduce Joshua Kobluk. So he'll be coming around here in a second. We're going to talk to him a little bit about his experience in the RDL. He is the liquids representative. And here he is. So Josh, introduce yourself.
Hi guys, I'm Joshua Kobluk. I'm the liquid propulsion technical representative for the RDL. I sit on the technical board. So the technical board is students and teachers who look over the technical excellence and technical leaps in the RDL. It is consisted of different leads for different subsections. So you have solids, liquids, flight vehicles, ground operations, safety, stuff like that. So I head up the liquid side of things. I am a third year. I have one more year left at college. Currently designing a liquid engine right now, and I've helped with this rocket and the previous rocket Altair. I was test team for Altair for about 2 years before we went to launch last semester, and sadly ended up in a fireball on the pad. But we learned an incredible amount of information from that launch, which we're now using to launch this rocket. So I and all my team members from Altair wish this rocket the best of luck.
Perfect. So, as you already stated, you played a role in Altair. How is your role in Altair playing into Deneb and your experience?
Yeah. So Altair was a huge deal for Embry-Riddle. Altair was the first liquid rocket that we designed, built, tested, made infrastructure for, drove out here, and attempted to launch. So we got all of our first out of the way with Altair. Altair had quite the journey. It started half a year before COVID, and it got crunched by COVID. And sadly, the team that was supposed to launch it graduated during COVID. So it was handed down to the class of sophomore and freshman. And I came in as a freshman that year and got on to the team my second semester. And from that, we really started, learning the lessons. We spent about a year trying to get the rocket just working again. Having the rocket sitting there from COVID really did a lot of stuff to it. So we had to learn how to pressure test the rocket. And then after that, we had to get it vertical to actually test the rocket. So we had to figure out how to put it on a test stand, what test stand we had to have. We had to design test stands for this rocket that we didn't have on campus at the time. So, we had to build a test stand for the rocket, and, every weekend we would have a boom lift operator come down and help us, lift this 150-pound rocket up into the air and set it on this test stand. And, all this stuff is stuff that we were constantly learning. And that rocket ended up having a failed test in the middle of the year, and it ended up getting pretty destroyed. It got bent in half in an accident.
First, let me stop you. So what was your feeling when, I know you were there when that accident happened, what went through your mind, and how did you all recover from that?
Yeah, so for everybody watching the stream, I think you all have that one thing that you do in life that's almost like a child to you. And for us, it's these rockets. And I think I literally put blood, sweat, and tears into that rocket, working on it in the summertime, bashing your knuckles off of the cross beams of it, testing for days on end and stuff just not working. It gets frustrating. But watching it have that catastrophic failure in front of us, was absolutely devastating and horrible. But it helped the team. We rallied back and rebuilt it and made sure to rebuild it stronger. And, took some of the lessons that we had from before that catastrophic failure, and we used that. But after that catastrophic failure, we came back strong, rebuilt it over last winter break, and came back, tested it a year ago to this point, and we had our first ever successful vertical hot fire on campus. So that was one of the first that Altair helped us with, was, how do you secure a rocket to the ground that's supposed to be flying? And that's a pretty big deal with something that, has an engine large enough to lift a car. So, all of these firsts is, lessons that we learned and passed on to the Deneb. And, all of the stuff that they have changed has helped with that. They built a new test stand that is an upgraded version of the one that we were using. The structure of this new rocket, is so much better than Altair's. Altair had a single structure that spanned the whole rocket, and all of our components were set into that structure. This rocket, the rocket itself is the structure. So the tanks are structural tanks. That means that not only do they hold the propellant, but they also hold the rocket up. And that's a big deal when it comes to saving weight and space. Another hilarious lesson was that the second time that we went to go launch Altair, we couldn't secure a trailer to send it over. So we actually took the rocket and put a mattress on top of my truck, and we strapped the rocket to the top of my truck and drove 8 to 9 hours with the rocket on top of my truck.
We should upload some rolling shots of that. We
Yeah.
got some cool rolling shots of that also, so we need to upload those to YouTube so you guys can check those out.
Yeah, but that was funny, but it was horrifying having to drive this rocket across country, on top of your truck. And that was one of the main things that they changed about this rocket, is this rocket can be broken down into 6-foot sections. So it is, super easy to move around, and it's super awesome just to deal with. Altair had that internal structure, like I said, in an outer shell, and you'd have to integrate the two of them. And it was about a 30-minute process just to put the rocket inside of itself. And like I said, this rocket is the rocket. The internals are the externals, so everything kind of just fits together nicely. So, we've learned a lot from Altair, and hopefully that'll help us get off the pad and get one step better than Altair. So,
Awesome. Another question I have for you is, what is your favorite part of the Rocket Development Lab?
oh man, probably my favorite part. As a freshman coming in, my favorite part was the ability to do these complicated tasks as a freshman, as an undergraduate and a freshman. I came to the school for the RDL, And I was in the RDL for about 2 weeks before I got hands-on with my first liquid rocket, and I fell in love. And it was my second semester at college. I mean, I'd only been at college for a semester, and I had no clue what I was talking about with rockets. And they put me on Altair's test team. And, you know, I was in the hands of a capable TCON, but still I'm dealing with high pressures, propellants, you know, stuff that could go wrong if I screw up. But they're trusting me. And as a freshman, that was my favorite part. But now as a upperclassman, my favorite part is, you know, providing that for incoming freshmen and sophomores. You know, I love the look on their eyes when they come in and, you know, realize that they're touching a rocket, or they realize that they've just assembled their first igniter, or, you know, they've realized that they just saw their first hot fire, and like the feeling in their chest after they get to, you know, see their first rocket launch. And it's just totally awesome for me to see that and see the excitement in all these students' faces. So
Yeah.
that's definitely my favorite part.
And we're all getting the jitters today. That today is a big day.
Oh yeah.
It's gonna be huge. So we're all getting that freshman first time kind of vibe all over again. And the freshmen themselves, they're very excited for this as well. It's gonna be an amazing experience. And an update on that. So as of right now, we are still waiting on avionics to reach the vehicle. We are waiting on the nose cone. Once the nose cone and avionics are integrated into the flight vehicle, we will be able to go start working through procedures, doing leak checks and all of that, and then from there we'll be about 45 minutes out of launch as well. So if you have any other questions about updates or anything, just let us know. We'll answer those for you. So we are going to get into a little more than just talking. We've got some props over here that we want to talk about. First of all, we want to discuss this bad boy. So this is Deneb's engine. It is Janus 4. You want to describe some components of this?
Yeah. So if you wouldn't mind passing me that prop. Yeah. So this is our Janus line of engines. So at our school, we have a few different engines. Currently, because of the chamber types that we use, we named the injectors. So our current designs is Janus, and Janus is a pintle design injector. So a pintle means that there is a tube that sticks into the middle of the rocket, and that gives us our oxygen, and then there's a little gap around that tube, and that gives us our fuel. So this injector provides a super stable burn. It's super awesome for undergraduates like us that don't quite have the best tuned engines. And we know that, you know, if we throw propellant in here and we screw up just a little bit, it's not going to explode. It's a little bit more forgiving. We have another injector type on our Kairos engine, and it's called an impinging doublet, which means that we have two holes that pair with each other, and then those holes are paired all the way around the engine. So there's about 8 sets of holes around the engine. Each one of those holes has one oxidizer and one fuel hole. So those two holes smack into each other, they combine and create a cloud, and then that cloud is combustible. So talking about our Janus line of engines, this is the line of engines that we have made for flight vehicles. So as you can see here, this is the Janus 1 injector and chamber. Our chambers are composite, which is why we call the injector Janus and not the chamber, because we have to replace the chamber every single time that we fire it. So the Janus 1 injector was made to fly on Altair. It's about a 6-inch diameter injector with about a 3-inch chamber. And you can see the size comparison between Janus 1 and Janus 4. So now we look at Janus 4. Janus 4 is what we have, upgraded to using all the knowledge that we have learned from Janus 1, 2, 3, and 4. And Janus 4 is a larger thrust-producing engine and just a larger engine in general. So Janus 1 was designed to optimally produce about 1,000 pounds of thrust. Janus 4 is designed to optimally produce around 2,000 to 2,500 pounds of thrust. These engines are also designed for different flight heights. So Janus 1 is optimized for a maximum flight height of 30,000 feet. Janus 4 is optimized for a maximum flight height of 150,000 feet. So you can see the difference in the diverging section, that's this end section of the chamber. The difference of size is huge, you know. It's about another 4 inches difference in this engine. The Janus engines are awesome to us. We're actually continuing these line of engines with the engine that I'm designing, Janus R. But we're going to probably continue using these Janus engines and just keep updating them because every iteration we learn a whole bunch that we can then move on to the next iteration.
And our Janus line of engines will probably be what takes us to the Carbon line as well, which is absolutely fabulous. So another thing we want to talk about is the fact that this is a fired Janus 4. And we want to talk about the fact that why is the throat area different in this one compared to this one? And that's because we have a phenolic throat insert. And if you would like to talk about that as well.
Yeah. So here you can see the actual Janus 4 chamber. This is a real chamber that we made in-house with our own hands. And then fired it on our own test stand. Kind of talking about the parts of an engine, you have the combustion chamber, which spans to about here. The combustion chamber is where we feed our fuels into the engine, and then the explosion happens. So this part contains the actual explosion, and then we have our throat section. So our throat section is aided by a bunch of semi-complex math. So we break the sound barrier with our combustion gases at the throat. And then we have something called the diverging section. So this section downstream of the throat is the diverging section. The diverging section is the area that the thrust pushes against to move our rocket into space. So the diverging section takes those gases and continues to speed them up. So at the exit of the chamber, our gases are moving about 3 times the speed of sound. So that's about as fast as a jet flies. So looking at our chambers, the throat section, which is that section in here where the gases are moving about 1 time the speed of sound, that section sees the highest heat, the most pressure, and the fastest flow in comparison to the combustion chamber. So that section, because we are using ablative chambers, that means the chamber burns away as we fire it. Because that section is the most aggressive section in the chamber, it burns so much faster than the rest of the chamber. So again, upgrading our Janus 1 chambers, we would fire them for about 10 seconds, and the throat would be about twice as large as it was to start. We would lose about 400 to 500 pounds of thrust just from firing it that long. And when you're talking about a flight vehicle, that is an enormous amount of thrust to lose. That's half of your thrust. And it's especially enormous when you're talking about a vehicle that's, 150 pounds. So one thing that our fabulous teams back at the RDL have done this last semester and last year is they've been looking into phenolic throat inserts. So a phenolic throat insert is actually something that NASA started. They started whole phenolic chambers, but we did a research on it and we said, we don't have the money to spend on full chambers, and it's actually more beneficial for us at least, to only have the throat insert in. So what we've done is we've taken this phenolic compound, which is a resin epoxy, and we take that and we impregnate silica fibers. So those silica fibers impregnated with that phenolic resin, we then take those and squish them down into layers, and that gives us a puck. So that puck, we then post-machine it to a throat size, and now we're left with this ablative material that's super strong and ablades at a very slow rate, and is just, 10 times better than the other ablative material that we used to be using. We then take that puck, we'll throw it into our chambers, and then we'll do this overwrap on it. So the way a chamber is assembled is we have a starting mold. So we have a huge metal die mold that we set up on a table, and then we place the throat insert in the throat section, and then we start wrapping the rest of our ablative wrap. So we wrap our chambers and we do a few wraps going down, and then once we are satisfied with the thickness of the ablative, we then go into our overwrap. So our overwrap is carbon fiber. We do carbon fiber overwraps. This chamber right here is wrapped with a not pre-impregnated carbon fiber. So it's called a wet layup. So that means you have dry carbon fiber that you lay down onto it. And then you take a little sponge and you put the epoxy on top of it. However, the chamber that we're flying today, we're actually using pre-impregnated carbon fiber, which was graciously donated to us by Firefly. So shout out to Firefly, thank you guys. We are going to be flying some of the materials that you guys have donated to us.
I have a question real quick.
Yeah.
So one of our fine viewers has asked us, how do we secure our injector to our chamber?
That is a great question. So let's look back at Janus 1 here. So you can see that the injector itself is kind of this section here that is inside the chamber. We then have this huge flange. You can see this huge silver flange here.
You can also see it on this injector as well.
Yep, and you can also see it on this injector. So you see that silver flange at the top. So that silver flange is a aluminum flange that we pre-machine, and then we set into our chambers before we do our final wrap. So you can see it fairly decent. Let me get a little closer to the camera. You can see it fairly decent here. So you have your ablative material on the inside, and then you have this inside flange. And that inside flange is what transfers all of the thrust from the chamber up into our rocket. And then we overwrap it with our carbon fiber. And the carbon fiber is what gives it the actual strength, and then the flange is just what connects it to our injector, and then our injector is then connected to the base of the rocket.
Perfect. That's great. Yeah, so we have wrapped, did you talk about how much it's ablated? This is our first time fired chamber, and it ablated like thousands. Like barely anything. So you can see on this chamber, all of that silver scoring is the ablated material. So that's the material actively ablating away. And you can see a whole bunch of streaking. You can see this kind of streaking down the chamber, and that's caused by all of the flow, the high-speed flow that's moving through our chambers, comes together in different areas and creates higher pressure temperature areas than other areas. You can kind of see this like on the side of a mountain, how water will kind of flow down different paths and will create these streaks down a mountain. You get the same exact thing in a rocket chamber. The awesome thing is, if you guys look down inside of there, there you go. You can see it almost looks like a perfect circle. That's because it is. It does not have any of those streaks, and that's the phenolic throat insert. So it's awesome looking at this chamber because you can see the difference between the different materials that we use in the chamber itself.
So the wrap that we have before the throat works really well because even though it's high temperature and high pressure, it's pretty much no flow velocity. So the gas isn't moving very fast. But once we move down towards the throat, you can actually start seeing that material degrade away more and more. And then we hit the throat insert, and there's no degradation at the throat insert, which is super awesome for us to see. That's the thing that you want to see in rocketry is you do not want to see your throat to, ablade or degrade away. The more it degrades, the worse performance you get out of your engine. So, like I was saying, you can see that throat in there is super circular, and it's super awesome. And that's the best part of this engine. And then after the throat, you can see that the expanding section, starts getting some of that streaking again. But because it is a lower temperature, it doesn't streak as much as it would at the throat, where it's, higher temperatures, pressures, and velocities. So, the throat insert is doing its job, and we're super happy with the phenolics team and all the work that they've done this last year.
Yeah, it's pretty fantastic. Shout out to the phenolics team. This is awesome. It's fantastic. So, going back into some injectors, I know that you were red team for the day that we detonated Janus 3.
Yeah.
So, can you explain a little bit of what happened with Janus 3 and I guess maybe what happened and maybe how we fix it or take things into account now and what it did to the injector itself?
Yeah, sure. So a step back in history and kind of, getting incoming people excited about the school. I came into the school and we had Janus 1 designed, made, and tested, which is our first iteration of the Janus injector. Janus 2 was designed, but sadly never made it to the machining phase. But they then took that design and turned it into Janus 3. So they took the design, improved it, and sent it to machining. Janus 3 was meant to be a water-cooled engine. So, stepping back to the throat inserts, instead of using ablative material and those really nice throat inserts, we actually use a copper chamber. So the chamber is machined out of a huge piece of copper. We machine it away, machine it down to look something similar to this. And then we take that copper chamber and encase it in steel. And then in between that steel and copper chamber, we flow water, fairly cold water at very fast speeds. And that allows us to keep the chamber cool. So this was the injector for that chamber. And sadly, on the day of testing, and again, this is my freshman year. I was only a freshman. I'd been in the RDL for a few months at this point. And they said, hey, would you like to be test team for this engine? And I said, oh my gosh, of course. So I got to be out there actually turning the valves and doing stuff with this engine. But we got to button push, countdown went, and it blew up on the stand. It produced a shock wave that set car alarms off a few neighborhoods over. It produced about 10,000 psi, which is enough to send a chunk of metal through just about anything. But thankfully, because of the safety procedures and the safety protocol that we have in the RDL and everything that we have set up for rocketry, nobody was hurt and, barely even startled, honestly. Like, we were all sad. We were like, oh, no, it blew up. But everybody's like, oh, but we're all okay. So the next thing was figuring out what to do. So, the test stand was on fire. We've leaked fuel over everything. So again, going back to safety, me as a freshman, I was able to go out there, approach from a distance, and help put these fires out. The next thing we got our hands on was the chamber and the injector. So this is the remnants of the injector, if you hold that for me. So the injector splits up into 3 main sections. So you have the pintle, you have the back plate, and you have the face plate. So the injector, flip that around. Yeah, there you go. So the injector goes together like that, and you can see that this plate is no longer flat. So the explosion ended up sending this pintle and pintle post back through the stand about 4 inches, and it shifted our feed system back enough to knock our tanks off of their stands. So one of the main lessons that we learned from this is to not secure all of your components where they can blow out the back of your engine. The other thing that we learned is that, you know, you need to have some failure modes for an engine. So, you know, everybody thinks about making the engine work properly, but what about failing properly? You know, when this engine blew up, it ended up throwing the chamber down range about 8 feet, and that chamber was about 40 pounds. So that's a lot of energy to go into that. Not only did it do that, but it bent this and sent the pintle back. So, I mean, all of those things are then counted like non-usable, they were all scrapped, and they've all kind of just turned into show pieces. But on our new chambers and new injectors, we have set failure modes. So it's, you know, making the engine work properly, but if it doesn't work properly, it's making the engine fail properly. So on the new injector design, I don't believe Janus 4 has it, but Janus R is going to have it, where we'll have failure modes in our bolts. So our bolts are going to have specifically calculated areas so that if we do ever overpressurize our chamber, they're going to shear and everything will just kind of flop to the ground instead of sending stuff everywhere. So that means that if we fail, I mean, I hope we don't, but if we fail, it won't be catastrophic. It'll just be something where we just have to buy, you know, 20 new bolts instead of a whole entire new chamber. But looking back at this, another thing that we learned is that rockets are hard. And, you know, you can design this injector and design this engine, you know, perfectly with math, but it may not work well in, you know, actual testing. The main reason why this thing failed was actually something that we overlooked entirely. It was our ignition system that made this fail. So we were testing this new chamber, and we were also, at the same time, testing a new igniter. So currently we use Estes motors to ignite our engines, and the thing that we were frightened of is with the copper chamber, we were scared that the Estes motor was going to burn a hole through the wall of our chamber. So they put a flame diverter on the front of the Estes motor, and that would help spread the flame out in the chamber and kind of give a cooler but larger flame to ignite our fuels. Sadly, when Red Team was moving back to test positions for the test, and we chilled the engine, so that means we flow liquid oxygen through our engine, we shifted the igniter out of the engine about 1/2 inch, and that's all it took, was 1/2 inch. And that 1/2 inch made it where the flame was no longer shooting directly into the chamber, but shooting outside the throat a little bit. So what happened is we started flowing fuels into the chamber. The igniter was flowing out of the throat on one side and then flowed into the throat on the other side. And that flame front fed back across the top of the chamber and then fell down to the puddle pooling at the bottom. And when that puddle exploded, it blew everything up, sent the chamber down range, bent all this metal, and, you know, put our test stand out for the summer. So we've taken that knowledge and designed, you know, the new injector, Janus 4, and a new igniter system. So we used the old igniters for Altair. For this new engine, we've taken Estes motors and modified them, and then we use a 3D printed stand to hold them in the chamber. So these modified Estes motors will make sure that we don't burn through anything in the chamber, but it also makes sure that the Estes motor stays in the chamber. So these are super reliable and super awesome, and we actually haven't seen any issues with them yet, and we've actually seen the opposite. We've seen fabulous startups on all of our engines. So super awesome.
We have a question on the live stream. I don't know if you know this, but what are what are the combustion efficiencies that we're getting on our pintles? Do you know the answer to that?
Oh man. It changes. It changes every engine and every test. Um,
We're all undergraduates.
Yeah,
here.
we're all undergraduates. Let's see. Janus 1 was a fairly inefficient pintle. I can't tell you the exact numbers, but we definitely weren't getting the most efficient burn out of Janus 1. Janus 3 blew up, so we'll count that out. Janus 4 is sort of the same way. We actually screwed up some of the math on the mass flow rates. We're getting some pressure drops above our venturis that have caused our mass flow rates to fluctuate. So we're actually getting a lower OF ratio than we were expecting. So Janus 4 is actually less efficient than Janus 1 in terms of combustion efficiency, even though it's producing more thrust.
So I just got a message from one of our members that Janus 4 is about 75% off of calculated values. So if that answers your question, that's perfect. We also have a question about winds speeds. So we have a constant limit as stated by the RDL that we have 15 mile per hour wind limit. Today, as a projected weather forecast, we're only going to get up to about an 8, which is amazing considering the last few times we've been here, it's been quite windy as the day goes on. So the launch window from 8 to 4 p.m. isn't as much of a concern. We don't have to get it done like as soon as possible. We have as many tries as we can as long as we're prepared. But yeah, the wind is not going to be a constraint for us today unless some random wind gust starts blowing through here. So, is there anything else you would like to talk about in particular?
No, I'm just excited to see this thing go. I think all of us are starting to get antsy, getting ready for this rocket to fly up in the sky. We haven't had the best luck out here the last few years, so we're really hoping that Deneb just shows itself to us and is able to go up and back down safely. So if we get those two things right, then I think the day will be good for everybody.
Perfect. That's great. And I'm just going to give a shout out to Winston. You commented on here. You said what's poppin'. So we're having a fun time out here. Wish you all were here, especially some of the people that weren't able to make it out today that I know want to come out. Enjoy doing your schoolwork at home. And with that, we're going to take a quick break. We'll be back. I'll come back here in about 20 minutes to give y'all an update on what is going on. We have not heard anything about avionics as of yet, or I have not heard anything about avionics. So I will keep you all updated, and we're going to take a quick break. Thank you. All right, everyone. Hello, we are back. Just wanted to give you guys a quick update that we are almost ready for the vehicle to be completely assembled. They're doing some final packing on the nose cone as well as integrating avionics. The nose cone will be put onto Deneb on the rail, and you will see that shortly. Other than that, we're just on hold right now. I've heard from a couple of team members that expected launch is going to be a little after 11. Sorry for all the delays. However, we're getting closer and closer to the time for launch. It's going to be super exciting. Yeah, so I will probably come back in just a little bit when we finally start getting that nose cone integrated, and I'll bring 2 capstone members with me. One will be Jared Walker, and then potentially Zoe Brand. We'll talk to them as they have been on Altair and Deneb and are played very significant roles in this capstone as well. So, look forward to talking to you all again. Just submit any questions that you have. I hope you all are enjoying watching this live stream. This is going to be really, really awesome, and I hope you guys enjoy. So I'll see you guys in a little bit.
2, 1, 0.
everyone, we're back. We have just gotten nose cone integrated and onto the flight vehicle. Everything is packed and ready to go. Next step is for the vehicle to go vertical. So really exciting. We're getting closer and closer. After that, it'll probably be about 30 to 45 minutes until we're ready to launch. So we're gonna cut this casting around probably the beginning of LOX load, so that way we can get all the cameras set up and ready for launch, so that way you guys can see the cool stuff. But for now, we're going to introduce Jared Walker, one of the capstone members. Here he is.
Hello, hello.
All right, hi Jared.
Hello, how's it going?
Good, how are you?
Doing great.
How's your day going so far?
It's pretty awesome. Got up early and worked on a rocket.
Yeah, I mean, that's great.
What more can you ask for?
I know. Totally agree with that statement there. So why don't you introduce yourself, tell them what you do and what for the capstone and how much work you put in.
Yeah, absolutely. So my name is Jared Walker. I am a senior here at Aborted, and I've been working in the RDL for about 3 years now. I'm in my last semester of my senior year, so I'm getting ready to graduate and move on to the real world. I have been working on this capstone pretty non-stop throughout the entire semester. To put it in perspective of how hard my team works, I've put in like 250 hours, and I have the least amount of hours on my team, which that just speaks to the drive that the rest of my team has to get this rocket up here on the pad. So yeah, that's just a little about me.
Perfect. Awesome. And so what has your role been on Deneb itself?
Yeah, so as a member of the Deneb capstone team, I have been working on the nose cone as well as the flight modeling. So in terms of the nose cone, our rocket's going to be going really fast. We're going to be going between Mach 3 and Mach 3.5 at our fastest, and at those speeds, it's going to get really hot, and the nose cone is what's going to take the brunt of that temperature. So what we need to do is design a ablative, which is a coating that flakes off and pulls the heat with it as we launch. So my job was to look into different technologies and materials that we could use to coat our nose cone so that the nose cone does not get melted in the process of launching. Something that's important to note with that is that all of our avionics on board are in the nose cone. So if there is a hole in the nose cone that we didn't mean to be there, it's game over. So it's pretty important that we have that ablative for the nose cone. And then in terms of the flight modeling, I was in charge of pretty much seeing what our flight was before the rocket was actually made. So I took the thrust curve data that we expected to see out of our engine that was being manufactured at the time, modeled what we expected the rocket to be, and then used a simulation software called RAS Aero 2 to get all of the more accurate thrust measurements, our drag coefficients, all of the values that you need to ensure that you're going to have a safe flight. And through that, we were able to get our certificate of authorization from the FAA actually back all the way in January. So it was really great to get that done. And as I was finishing up my flight modeling stuff, I was able to...
I don't mean to cut you off, but we got some vertical action going on here.
Let's go!
So we can check that out. You can run out there if you would like
Okay,
to check it out. So we're going to check that out, and we'll be right back. All right, so sorry to run off like that, everyone. This is just a really exciting moment. We're now vertical. We'll be going into fuel load here soon. Launch is probably about 20-30 minutes out. So right now we're just kind of waiting until Jared gets back so we can interview him. Obviously, he's got to get out there and take those pictures and enjoy his rocket. So we'll just wait for a little bit. If you guys have any questions about anything that you want answered, just throw it in the chat. I see someone asked about lock fluid with manual fill valves and vents. If it's filled that way, yes it is. But we already had someone answer that question for you guys. Thank you, James. If you have any other questions, just either DM on Instagram and I'll check that out. And if not, then just stay tuned. We'll be back here in a little bit once ever Jared gets back. So stay tuned, everyone. This is going to be a really exciting day. Thank you. and we have Jared back again. Yippee.
Hello again.
So we have a couple of questions that were asked in the stream. We have, is there a name for an engine?
Yeah, so the name of this engine is Janus 4. So it's one of the most recent things in a line of our engines that we manufactured here on campus. Previous rockets that we have attempted in terms of liquid rocketry have also run Janus engines per name, but they're not the same design. So we actually had Zoe Brand, who I think might be coming on here to talk in a little bit. She fully designed this new engine herself, and she was part of the manufacturing process all the way through it. And she's one of the reasons that our capstone team is here right now. So, yeah.
And then the next question is, what is the difference between propellant load and gas load?
Okay, so pretty much propellant load versus gas load. We have two propellants on board. We have our fuel, which I believe is what you're looking for gas, unless you're talking about our GN2 fill.
I think it's
Okay, so your propellants are your liquid oxidizer, which for our case is liquid oxygen, and then you've got our fuel, which is kerosene. So pretty much think of refined gasoline that you would put in your car. And then for gas fill, what we're talking about is what provides the pressure from above on the rocket. So we have what's called a carbon overwrap pressure vessel in the top of the rocket that we set to a really high pressure. So we have it set to about 5,000 psi. So to put that into perspective, your car tires have about 30 psi of air.
Yeah.
So what gas load is talking about is loading all of the gas into that COPV, and then when we're ready, we have what's called a regulator downstream of the COPV.
What is the COPV?
Carbon overwrap pressure vessel.
Cool.
That's what holds it, and that's the only thing on board that can hold anything even near those pressures. That's a lot of pressure, and we don't want that kind of pressure in our tanks. Our tanks would very much explode if they saw that pressure.
That's not
so
what
we have a regulator that regulates the pressure that we have in the tank down to what we want in the tanks. So what we want is about, I believe, 500 psi is what we have it set for our tanks right now. And that's what the regulator's job is. So yeah, we fill the gas into the COPV and fill the tanks and then launch a rocket.
Cool. Awesome.
They need Jared for a photo with Dr. White.
Okay. You want to go take a break for a photo real quick?
I will be back again.
Taking a photo break yet again. Guess you can see if there are any other questions in here. I guess I can explain a little more. Briefly, there's a tractor outside. Oh, it is? Are they bringing the locks out?
Oh, it's a big cryogenic tank.
Okay, so if you can see probably shortly in the stream, if we have the correct view up, you'll be able to see the tractor that's carrying out the liquid oxygen out for our prop load. So that means we're really getting close. You'll probably be able to see it here shortly. Oh, here it comes. You'll see it coming in view. We'll just wait a little bit for Jared to get back. If you guys have any questions, as I said before, just throw them in the chat. I will check Instagram to check and see if anyone has asked me questions on there. I will also send out an update. We're getting really, really close to our launch time. Once LOX load is in process, LOX load will be complete in probably about 10-15 minutes, and then soon after that it'll be 2 minutes until we launch. We're going to have some really cool onboard footage for that as well, thanks to Kyle and his goggles. We have that all hooked up for everything. We'll move this camera that is actually filming me right now out to look at the pad, so you'll be able to see that and hear it with audio as well, since that's where our microphone is. And then a few other things as well. Yeah, so if you guys have any questions or anything, just send them in the chat. I'll check here. Let me get Tom over here. I can see if Tom is available. He's very busy right now since he is the DAC personnel. So I will see if I can get him over here to talk real quick. But it might be unlikely that we get to see Tom. I can get him over here to say hi. You can come back.
Okay.
Jared's back.
Hello. I feel like paparazzi, except I have to go to the paparazzi.
All right, perfect. So we finished that. Do you want to finish explaining what you did for Deneb, or did you finish it?
Yeah, I pretty much finished just like the flight modeling. I was trying to get what our estimated apogee, which is our maximum altitude, drag coefficient, our putting in that thrust data to make sure it's as accurate as possible, all that kind of stuff. So
All the cool
flight
stuff.
modeling.
And I'm actually recruiting Jared's help along with Duncan's for future Mountain Spirit rockets for the Block 4 rocket that's going to take us to space. We need his expertise, so it's perfect. I guess we can move on to the next question that I have for you. So you were on both Altair and Deneb.
Yeah.
So what has changed between the two of them? What has been most noticeable between the teams?
Oh yeah.
And what have you guys done in order to make this rocket successful compared to Altair?
Yeah, so really what I think makes this rocket successful in comparison to Altair is the technology that we have developed since Altair because of Altair. So just a couple things to name a few. One of the major improvements that we've made here is that our tanks that hold our propellants are structural tanks. So what that means is that the tanks themselves can support the weight of the rocket while it's standing vertical out on the pad. So Altair did not have structural tanks. So what we had to do there was use metal C-channels that went all the way up and down the rocket to support it. And those, yeah, it was a noodle is what we called it.
You carry it and there's some sagging.
Yeah, that was a mess. But that adds a lot of mass, and the heavier your rocket is, the lower it goes, and that's pretty lame. So we learned to make structural tanks so that we can go higher, go faster, have more fun. Some other things that are really important is that our fin can design is totally different than what we did for the fins on Altair. So what we use here is we have these 3D printed outlines of what you would see on a rocket fin, right? But the inside is empty and we fill it with a Nomex honeycomb. So what that does is it brings the weight of the rocket down. Again, really it's all about how heavy your rocket is.
Yeah.
And it brings down the weight, and also it is incredibly strong. Honeycomb is used in pretty much every commercial airliner engine you've ever seen to keep the engine intact. And similarly for us, that helps keep our fins intact, brings down on the weight. What are some other things? Oh, one of the things that I said that I was working on, the ablative for the nose cone, that's a brand new technology as well. We didn't have an ablative on Altair because Altair wasn't going nearly as fast as our rocket's going to go, or as high. Yeah, definitely not as high. To put that into perspective, we should be burning out, which means our engine is going to cut off 18 seconds into flight, and at 18 seconds into flight, we'll be at about 30,000 feet, which was the maximum altitude for Altair.
Yeah.
That's and then we have another 2 minutes of coasting through from the momentum of the rocket.
Yeah. And also up until burnout, we're probably going to have some live footage from on board the rocket, so that'll be really sick if you guys, if the camera doesn't cut out beforehand, you'll be able to see engine burnout as well, which is going to be so fabulous.
Yep.
So, looks like we have. So you mentioned that this is Block 2, and you said that you're recruiting for Block 4. Does that mean Block 3 is in the works? What are the milestones that for that vehicle leading up to the space shot? So Mountain Spirit is being a little bit reorganized at the moment by me and my co-lead Hayden Patterson, along with our engineering leads and some other business people as well. Block 2, originally in the Mountain Spirit program, there was Block 1, 2, 3, and 4. Block 4 was is supposed to be the space shot with a liquid vehicle. So things are kind of changing just a little bit, giving it more structure. So we're not exactly quite sure everything that is going to be specified for Block 4 as well as Block 3. We're basing everything off of Deneb's success and the technology that they have acquired to push forward in our other vehicles and see what works and what doesn't. This summer, actually, and beginning of next fall, is when we're going to be really doing a lot of trade studies into what the final vehicle should be and what we are capable of doing, as well as the technology that we need to develop and the different groups that need to be coming in. So if any incoming freshmen are watching, we need you. We'll be looking for you. And if you're excited and motivated, and even if you don't know anything, you'll learn a lot. I know I didn't know anything when I came here at all.
Absolutely. So. I think that the freshmen that are helping us out are crucial to the success of the RDL.
Absolutely.
We have so many interns, as they've coined that for themselves. We didn't make that up. That was Harrison, really.
That was Harrison.
But they are so helpful because sometimes you just need more hands. Mm-hmm. And they're here, they're absorbing the information so that when we leave, they have the knowledge so that they can teach the next generation. Absolutely. And it keeps going. So.
Yeah, and that's very valuable, which is what we're trying to do moving forward as well, as you guys are doing so well, is documenting everything that we're learning. So even after we're all gone, from what we've developed and what we've done, it will pass down to the next generations of the Rocket Development Lab, so that way we can still pursue success throughout the club. Incoming freshman here. Hello. We're so excited for you to be here.
Welcome.
If you are interested in joining the Rocket Development Lab and getting involved in Mountain Spirit, you can come talk to me and so many other people that are willing to put you to work.
Yeah.
We'll have so many other teams coming in.
Did you do the 3D printer?
No, I haven't.
Okay.
I haven't. I missed that
So
one.
there's a comment here from Jacob Jackson asking, are there any 3D printer components? There's a ton of 3D printer components throughout the rocket. I think the most notable really is the sled that all of our avionics are fastened onto the nose cone with. So in the nose cone, we have like this 3D printed, I guess you could call it just like a plate that has a little spot that we've carved out for each of our different avionics, which are the things that can tell us our altitude as well as our GPS location and things like that. And a bunch of different like small components throughout the rocket that we needed quick. And actually last night we were printing parts still for our quick disconnect mechanisms on the rocket. So yes, we use a lot of 3D printed components on our rockets, and that's not going to stop with this rocket.
Yeah, and even to add to that, I know I've walked in the RDL a few times, and there have been like 3 different printers printing at almost all times, getting prepped for this launch, even like at the last launch and at this one. And as Jared said, they've been printing, even as today, they need some rapid parts ASAP.
Yeah,
they've got them.
Absolutely.
Which is fantastic. It's amazing how technology has definitely improved. I think a lot of people who, especially back in the day, it's amazing.
I remember the first time I saw a 3D printer on like Instagram or something. I was like, how
gosh.
is that possible, turning plastic into
like
other plastic?
I know, which
It
is
was
also
awesome.
what this here is too.
Absolutely.
So this is a 3D printed model
Yeah.
of their engine. Let's see. So Winston is.
I'm interested in joining. How
Winston,
can
isn't
I?
it?
No, it's a different Winston. Sorry, we have another friend named Winston here in the RDL. We thought that was you for a sec. I am a freshman at San Clemente High School. Is there anything I can do to get involved? I don't know if there's anything directly as a freshman in high school that you can get involved with the RDL right now. You could obviously reach out to any of us on our social media platforms if you want to learn anything from us. And we can give you tips on what you can learn before you come to college so you're more prepared for things like that. But I do know that they were doing camps my freshman year. They still do the summer camps?
I think Dr. Briner is doing like the rocket program.
Oh,
like,
awesome!
summer camp.
Yeah, if there is,
That'd be something I could clarify with him.
100%. If Dr. Briner is running a camp, he is one of the main mentors that we have here in the RDL, and he would be an amazing resource for you to learn some stuff from before you get here.
Absolutely, for sure. I'm junior right now. We absolutely do.
Oh, let's go, Jacob!
Let's go! So excited to have you. I know.
What about old alums joining?
Oh, alums.
I don't know.
Old alums.
Yeah, alumni.
The Rocket Development Lab? Just a clarification on this question, Jason Payne, Julia's father. Your question is, what about old alums joining? I guess we want a clarification. Do you mean joining the Rocket Development Lab?
Like hands-on, or are you saying how can you support? Not exactly sure.
If you want to support, that's another thing.
Yeah.
If you want to support the Rocket Development Lab, maybe make some donations on our website at rocketdevelopmentlab.com. You can go all the way down to the bottom. There's a big donate here. I think it's up at the top also.
Yeah,
Here. Thanks
I
to
think you're right.
Julia.
Yeah.
Her and Cody Hawes made our website. And you can just go on there and click donate, and if you want to support the RDL that way as well. And if you also go on there, we'll have a big banner for our live stream also, but you've already found us. So.
Yeah, so next up I see Angel Gaming. Where are y'all launching from? We're launching from a location called Friends of Amateur Rocketry, far for short, in California, about 30 minutes south of Bakersfield, California. There's a launch site out here that these guys are volunteers for. They come out here and they have this facility for us to use. But it's up to us to get the rocket to the pad. They're not hands-on with us. They don't help us build anything. They just give us the resources that we need to use for the launch rails and things like that.
Yeah, and we've come out here for the past 4 attempts. So Deneb's last attempt, we came out here, Altair's first and second attempt, and we also came out here for the launch of one of our solid flight vehicles, Spectre.
Yeah.
Shout out to Spectre, we'll find you. Thank you, Mac, for the shout out.
Yeah, shout out Mac.
Woo!
That's the homie.
Thank you. Let's see. Hello to Lawrence and the whole group. We're watching you. Oh.
Hi, Lawrence's mom.
um.
Jared, it's Ari from the night before preview. Oh, what's up, Ari? We're leaving for camping. Oh, and yeah, you were helping us like with some of the panel stuff, right? So excited to see the rocket I worked on a little launch. That's awesome, dude. Yeah, super exciting. And I'm pretty sure you said that you accepted an offer here. So some of them will see you guys in the fall. Unfortunately, I'll be gone at that point, but you got them. So that's pretty awesome.
Yeah. So.
All right. Oh, hi, Cam. My sister.
Oh. Let me see. Okay, so I guess I'll ask this next question, and then I can let you go, and I'll try to find Zoe somewhere if she has to have some time. Who is on your team, and what are their roles? Like, how is everyone like working together with their different expertise? Because all of you are very intelligent, and you all have your very own fortes.
Yeah.
So. Who is doing what, and how is that making this rocket possible? Because
Absolutely.
you guys have been working day and night.
Yeah, we have. So as I mentioned, I was in charge of the flight modeling and the nose cone, as I mentioned earlier. In terms of my colleagues, we've got Benjamin Black. He was working on our test operations and creating a structure that could support our rocket when we're doing our vertical testing. Then we've got Zoe Brand that I briefly mentioned earlier. She was working on designing our engine that is actually providing all of the thrust that we're going to be using with the chamber, because she also helped with the chamber. She might have fully designed it herself. I don't remember off the top of my head.
Christopher, maybe.
Yeah.
Christopher. Shout out to Christopher.
Yeah, so there's them. Then we've got Duncan Shower. He's working on the avionics, and I've been working pretty closely with him because the avionics are integrating with the nose cone. And then we've got Kyle Dutcher, who is in charge of our structures, and he also helped out on the avionics side of things as well. And when I say structures, I'm talking about the fins and the structural tanks that I mentioned earlier. We've got Charles Flaherty, who is our fluids responsible engineer, who is in charge of designing all of the fluid systems within the rocket. So all of the tubes and the bendies and the stuff inside the rocket that gets fluids from one place to another, he designed the system that transports it. And then after that, we've got Dawson Damish. He is in charge of ground support equipment. And what that means is pretty much anything that is involved with the rocket that doesn't launch with it, he was in charge of making sure everything went well. So that's like the fuel panels and the upper tower panel and quick disconnects, which disconnect us from all of our propellant lines when we're ready to launch. Things like that. Who am I missing?
Tom.
Yeah, Tom and Dalton. No, I got Charles. So Tom and Dalton, they kind of both ran our data acquisition and instrumentation side of things, which the easiest way to describe that is the DAC system is the brain of the rocket. So everything that we command the rocket to do travels through the DAC box and into the rocket. And also with that, the DAC box also sends back the data that we receive from the rocket to make sure that all of our pressures, temperatures, and things like that are as expected. And if there's things that are not what we're expecting, the DAC box can automatically abort from those so that we don't have to rely on human aborts. But also we have the capability of doing that as well. So those two are geniuses. We wouldn't be here without them. Yeah, I think that covers everybody. Yeah.
Great. Awesome. Is there anything else that you would like to say before I let you go and enjoy your this fine day?
Yeah, no, I'm just glad that I get to be a part of something like this in my undergrad. Mm-hmm. A lot of schools don't have opportunities like this for students to get involved this hands-on, this early on. And I don't know, you probably mentioned it earlier in the stream, but all of the work that really the RDL does is all undergraduate students. We don't have graduate engineer students at Embry-Riddle at all. We have 2 or 3 advisors that we talk to like once a week, maybe, just kind of update them on what we're doing, but everything
Hello
else.
To them if they're watching.
Yeah, shout out Dr. Bryan, Dr. Sullivan, Professor Garrick, everybody. But yeah, that's that.
Yeah.
So.
Awesome. Well, thank you for joining us, Jared.
Awesome. Well, thank you very much.
Yeah, go enjoy your moment.
Will do.
And if you find Zoe anywhere, send her over if she's not busy.
Got it.
Thank you. Yeah, so, It's been great answering your questions. Yes, let's go Tom and go Dalton. Wow, you guys. So the launch vehicle will go, it was estimated to go around 150,000 feet in the original plans for it. However, due to some limitations and, actuals versus realistic, we know that engine burnout is going to be around 30,000 feet, as Jared has said. However, we're expecting, last I knew, we were expecting about a 90,000 foot apogee, but I could be completely wrong on that. And we can actually ask Zoe if she is able to show up, or I can bring someone else on that could answer that a little more thoroughly for you. All right. Yes, let's go. All right. I'm going to take a quick break. Throw more questions in the chat. We're going to have our engine lady coming on here soon, Zoe Brand. Hopefully, if she's not too busy at the moment. So get all your engine questions prepped. She will be the gal to answer those for you. So I'll see you all in a little bit. Thank you.
The Duncan has been caged. Zoe, how am I looking at on fuel load?
An inch left in the cooler. Sequence stop.
Fuel load sequence stop. That completes fuel load. Red team, gas bottle pressure, report. 500 PSI. Copy all. Alright, so we're gonna hold here until Duncan's done. I don't want to press a CAPV with him next to it. Can we have someone else go to the other team and get an ETA for when they're launching?
Coming down, by the way. Got about 10 minutes until they're launching. copy?
Copy all. Does anybody know where the metal zip ties went?
I think they should be in one of your totes, Kyle. Possibly toolbox 1.
Okay, so Duncan has completed his stuff. Alright, red team, load reg set. You said... Wait, hang on. Red team, could you set, that bottle is at 1500, right? 1500. Alright, could you set the load reg at, 1000? You're set at 1000 PSI. Alright, could we talk to the FAR guys? I want to press the COPV up. I talked to them about doing the step up. If they get confused, just hand them a radio. But I'm going to have you guys retreat like 100 feet while I press this, and then once pressures are stable, we'll come back to it. Austin is on it. Did I also get a doer pressure? Any word on doer pressure? Doer pressure is sitting a little over 250 PSI. Sick, thank you. Can somebody please check wherever the metal zip ties are at the launch pad?
The FAR guys are okay with it. We just have to make sure everyone is a safe distance away. The metal zip ties here. Ben has the metal zip ties here.
Okay, thank you. Can we get a all retreat 100 feet or safe distance? For awareness, there's a very small chance we put about 30 PSI in the fuel tank right now. Sounds good. Red team is safe. And confirm pad is clear. Here at the moment. Right, we're going to go ahead and press CPV GG tower. Is energized.
Fox breathe.
Alright, and we are coming up. Alright, red team, pressures are stable. Could you go back down and bring, or close the ISO, the press panel ISO, and fill the new connect the new 6K. I can walk you through the procedures if you need.
I remember what needs to happen. New 6K is clear debris. We are taking off the hose for the old 6K right now.
Copy. Copy.
Yeah, that hose has no pressure in it, just so you know. We're being safe.
Dawson, can you come back and grab the metal zip ties to do the mains so that we don't have to reapproach just to do the mains? You guys know that the zip ties go onto the white structure. We're trying to secure the orange hoses so they don't fly away with the rocket. The zip ties go on the white structure.
Copy.
Of the orange hoses as deep onto the barbs as you can, and then zip tie it so that they can't slip back off super easily, because they've just been slipping down the barbs constantly. Ben, we're just trying to metal zip tie the orange hoses onto the white structure. I understand.
To clarify, we are not putting zip ties on the barbs themselves. We are just putting it on the hose to support it for when the rocket lifts off, to tear the hoses off. 'em. 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 '
Hey, we got 5.
Hi everyone, we're back here and now we have our engine gal, Zoe Brand.
Hello.
Hello. If you would just like to introduce yourself real quick, tell them what you do,
Yeah.
who you are.
So I'm Zoe Brand. I'm a senior, of course, on Cygnus Suborbitals. I've been in the RDL for about 4 years. Started on Test L3 doing Red Team freshman year, and ever since I've been wanting to design an engine. And luckily I was able to do so on this capstone. So I fulfilled my my graduation gift to myself, being able to design this. So that's just a little bit about myself. So I'm the responsible engineer for the Janus 4 engine. I designed I did an iteration off of the original Janus design. I also designed and manufactured the chamber itself. So the injector is a pintle injector. We use Jet A and liquid oxygen. A few things I changed about this design is it's a
Here, if you'd like to demonstrate.
So I combined Janus 1 and the Janus 3 designs. As you can see in Janus 1, it's multiple parts. This is for manufacturability.
Hold that for you.
So we have multiple parts. That's a little bent from the right start. But we have multiple parts to reduce the amount of warping we get on the faceplate itself. One thing I did do is I completely took off a lot of the material on this faceplate to reduce the amount of warpage. And then I overall just made it to account for our mass flow rates for this engine. So we're working with an engine that is getting a total mass flow rate of 7.3 pounds per second. It has a thrust of now expected to be 1600. We had a bit of issues with our OF. You can design to an OF, but you know, mass flow rates might not work out completely. So we learned that during testing. So we have an OF of 2 instead of 2.4, but the engine still performs very well. So during testing, we got like 1,300 pound force. We're testing with an OF of 1.8. We changed the OF for flight because we're pretty confident with our Venturi calculator, and so we're going for an OF of 2. So that's just a little bit about the engine itself. But the chamber, I would have to say this is the most beautiful chambers we've ever made. Learned it from Matt Bobbin, freshman year. I was on the Bladips team. So this engine, I'm totally going to hit you in the face. It's okay. She's huge. This is an 18-inch long chamber. It is silica high temp epoxy with a carbon fiber overwrap. So this chamber is special because it also has in-house phenolic throat insert, which is very new. We've never done it before, and for at least our hot fires, we've seen only a 20 thou ablation rate on a 7-second hot fire. So that's awesome. We've never had anything like that. We've had issues in the past with ablation at the throat, and that's going to cause your efficiency of the engine to just completely go down. So the ability to have like almost no ablation at your throat is just ridiculous. So I think that's like a big feat for composites. And oh, we got a hot fire going. Is it hot fire or
I think it's a flight.
Holy moly!
Rocket, guys.
That's a rocket.
There was just a quick launch. I'm sure. I wonder if they probably.
Come on.
I don't know. They probably.
Still waiting for a
Event.
vent. Oh!
That's parachute.
Parachute.
That's stroke.
Parachute! Yay!
That's awesome.
We're seeing a couple parts. Everything's together. Yeah. Nose, cone, body. That's orange. Rogue. Yep, that I just seen orange. I don't see it. Not seen a parachute.
Awesome.
Cool.
Alright, well everyone's talking about that. What were we talking about?
And I see something shiny.
We're just going off. Yeah, I think we talked about a lot about the engine.
Oh yeah.
Do you have any more questions for me?
I do. So as a freshman, you're talking about freshman, you worked hands-on. I guess in that regard, we've talked a bit on the live stream about freshman experience, hands-on experience, and now she is the something happens good. Yay. She is now the engine gal, as I would say. So how did you go from coming in as a freshman, being like, I want to design an engine, like his hands-on test cell, to like actually doing it? Like, what did you do in order to get to that point for the incoming freshmen coming in, and even for myself, since that's what I'll be doing soon, hopefully?
Yeah, so I think the biggest thing was being something happened. The biggest thing is just being extremely hands-on and being like a go-getter, like asking constantly, hey, what can I do? What can I do to help? Just staying in the RDL and just like, honestly, it sounds like you're pestering, but you're not pestering anyone when you just constantly ask if anyone wants help, because honestly, we all need it. And so freshman year, I just kind of like stuck my nose into any project I could get into. Sophomore year, I was like, you know what? I'm going to think of how I can improve the engine we have, Kairos. So we had a team try to create a water-cooled jacket for our Kairos engine, which is a 200-pound force little engine, which is ethanol and liquid oxygen. That was a really good project, though we never made it because we deemed it just not really manufacturable. I learned a lot about heat transfer before I took it, and honestly, that was a lot of fun. It's like my favorite subject now. But it's just like thinking ahead of how I can improve, what can I do for the RDL, and just sticking your nose in everything. So I think that's kind of what you gotta do.
Yeah, perfect. I mean, take it from the best, that's for sure. So we have a couple questions. Someone said, what was that? It was a solid. Was it a solid?
Yes.
Yeah,
solid?
I think so. It's a solid.
Solid. I'm not too exactly sure what type of rocket it was other than solid. I don't know any specifics on it. It was another school, right?
Yeah, I don't know who. Sorry.
We can ask, I can clarify that for you after we let Zoe go. And then it asks, Logan Harold asks, are you using cavitating venturis on both fuel and lock side?
Yeah, we are using cavitating venturis. We have a pretty dope cavitating venturi calculator made by Kyle Dutcher, who's just a fluids master. And we've been able to validate all of our venturis based off of his calculator and just constant testing. One oopsie we had during testing, and what we figured out is when we actually used liquid oxygen and we did a hot fire, we had the wrong density of our liquid oxygen. And we were able to account for that for our later tests and now for flight. So
perfect. Awesome. Cameron asks, how do you prevent a hard start?
Well, to be honest, it's a lot harder to hard start when you are vertical, but it is all with the timing of your engine, or timing of your propellants. So we look for a 40 millisecond difference when we're sequencing our engine of both propellants. We do locks first and then fuel. And we sequence, of course, with our chamber off and with GoPros just pointing right at the injector. We use a pintle tip that is a through pintle, so that means it's just going straight down, and we're able to see exactly when the two propellants are impinging with our GoPros.
Awesome. Great, as well as our Phantom.
Oh,
cool
and
Phantom.
our Phantom.
Our
We
Phantom.
have a Phantom.
Shout out to Phantom. What else do we have here? How's your air breathing project coming along? It's not. Women in STEM. Thank you, Haley. Call us out. Do you chill in the Venturi prior to flowing through it?
We chill in our Venturi. Our Venturi is right below our tanks, so it is chilled in, and it's above the LOX main, so it's constant chilling before we actually are flowing propellant through the engine.
Interesting. Very interesting. I didn't know that. Great. Awesome. All right, and I have one more question for you because I know you've got a lot of stuff to do and you're getting a little antsy.
I have sea legs right now.
It's almost there, right? It's so close.
Everyone's like either sick or going to be sick, and we're just all anxious. It's crazy.
Yeah. My last question for you. I was just about to ask this question. What are your plans after graduation?
Well, I'm going to be going to Purdue, and I'll be working at Zucro Labs, working on rotating detonation engines for 2 years for my master's thesis. So I'm honestly really stoked about it. I wasn't sure if I wanted to do my master's or not, and I just said, you know, well, I got in, and I visited the school, and honestly, I was pretty excited. So I'm going to go ahead and... Looks like they need me, so I'm gonna go.
Awesome. Yeah, thank you, Zoe.
All right, thank you guys.
Yeah, thank you, Zoe, for coming on here. All right, so that was Zoe for everyone. She's very, very awesome. She's definitely our engines gal, and we have a lot to learn from her, and it's a little unfortunate that she's gonna be gone next semester. But I'm so impressed with all of you. Proud of you all, Zoe. You're amazing. Zoe is amazing. We all know that. Anyway, how far out are we? We know?
About 30 minutes from launch.
All right, we're about 30 minutes from launch. I will come back on here about around the time of LOX load, or I can bring some other people on here if they are not busy. But I'm going to let you all go and wait a little bit, see what's going on, and I'll update you all in a little bit. But it's looking about T-minus 30 minutes. So... let's keep our fingers crossed for them. All right, thank you.
On recovery. Jared. Let's go! And last but not least, Ben. He said, let's go. Oh, I think I talked over him. Alright, any qualms, reservations, or anything that wishes to be said? Speak now or forever hold your peace.
I think that means go.
Alright, team, we are go for flight. Entering LOX gas load final prep. Red team muscle reg verify set at 120 psi.
So I'm opening pressure panel ISO.
Please.
Okay. All right, everyone, it's getting down to that time. We are actually entering LOX load right now. Charles Flaherty just gave the go for launch. We are good for flight, and they're entering LOX load, which means it will be about 15 minutes until we are taking off. So I'm going to end my hosting here. We have a few cameras that we need to get set up, make sure that everything's all good, and we're go for flight. So getting a little jitters over here. I can't imagine what the team is feeling right now. I'm sure they're extremely excited. This is, as I keep saying, it's going to be a massive day. So that'll be great. Thank you everyone for watching us host today. It's been fantastic talking to different members of the team, and we will chat with you all later. Thank you very much. Bye everyone.
team, Locks Tower Man ISO, verify closed.
Tower Man ISO is verified closed.
Red team, cryo gloves put on.
Dawson's a running.
Alright, red team, verify locks door clear debris and connected to locks panel.
Door is clear debris and connected to locks panel.
Red team, locks door, report pressure.
Pressure is sitting at 250 PSI. Gloves are being donned. Okay, we are donned.
Alright, red team, locks door, hang on. Alright, can you open it fully and then go find the halfway point? So open fully and then use that to find how many turns halfway is. I want it open halfway.
Okay, will do.
Want to recirc as well?
Igniter is assembled.
Red team, igniter leads, rub and check for sparks. And Dawson, while we're out here, I want photos of all the cuties that you can reach.
Before I stay out here.
Somebody talked over somebody. What did you, I want red team first and then whoever spoke second.
No sparks.
Is it okay if I go and take pictures, or would you prefer I stay farther away?
You're fine until I call all retreat. Alright, red team igniter, secure in test position.
Igniter is secured.
Make sense leads connect.
Since leads are connected.
Can we verify the arm state of the DAC box?
Since was still armed, it is now disarmed.
We saw good continuity across the sense lead, so good work, guys.
Sense leads are connected.
Copy all. I'm thinking. Alright, just so you guys are aware, there's going to be a loud noise above your head, and then I'm going to have you do the load rate set at 5,000 PSI. Actually, we're going to move that. Hold that command. All, prepare to retreat.
Up on the rocket.
I understand that. Red team, remote camera, start recording.
On Kyle, but every other camera is recording.
Hey Charles, I'm gonna retreat real quick, do your thing, and then I need to head back out to finish setting up cameras.
We're about to arm the ignition leads and DAC box and go.
Can I have a few minutes?
Hold here.
And just so you know, Charles, ignition leads aren't connected.
Sorry, are or are not?
Are not.
Great, thank you.
I'm not done, I'm just checking that the live stream camera started.
Levi off the tower.
Live stream cam is started. I'm going to start the normal camera, and I'll be good to go.
Hey Kyle, let me know when you've done that, and we are good to rock and roll.
5900 PSI.
Red team, loud noise, then I'm going to GHE tower ISO, and then you're going to set the load reg at 5,000 PSI. GHE tower ISO de-energized. Alright, red team, load reg set at 5000 PSI, 5,000. Alright, all prepare to retreat.
We still need igniter?
We're working on it.
Copy that. Reg is set at 5000 PSI.
Alright, red team, all retreat. That means far in the bunkers. Not red team retreat, but everyone else. Red team, ignition leads, connect.
When we say we retreat, all miscellaneous personnel go to bunkers. We have one FAR guy staying out with us.
Team, ignition leads, connect.
Ignition leads are connected.
Red team, DAC box arm. Alright, I'm going to start LOX load here. Flight control, all switches and keys off and safe. Flight control, prop flow enable on, prop flow enables on. Flight control, LOX load sequence start. LOX load sequence has started.
You want recirc on or no?
Let me get to a stable pressure on the doer, and then I will let you know.
Copy.
Doer fully open, quarter turn back.
LOX doer is fully open, quarter turn back.
Red team, doer pressure report.
Doer pressure is sitting at 130 PSI.
Red team, give me a research, repress circuit open, please.
Test circuit is open.
That's not a full open, that's like 1 or 2 turns, correct?
No, that is a full open on recirc, quarter turn back.
Hey, give me a half open on repress circuit.
Lower dome is chilled in. Upper dome starting to chill. Further actions on the LOX doer?
Not quite. Red team, prepare to retreat. retreat.
Yeah, I'm trying to get him out of here.
We are about a half full on the LOX tank.
Pad is
Dalton, repeat.
pad is clear. B.
Loading gas. Alright, we're low on bottle pressure. I am stopping LOX load. Red team, prepare to go back out and hot swap the gas bottles. Red team, I need you to approach and go ahead and swap the G&2 bottles with a new 6K. The new 6Ks are in the far bunker. Alright, so go ahead and disarm the DAC box for me, please.
Still one new one over here, right? At the back near the last guy rail?
Is it noted as full, or 6K SI? It should be noted as 6K SI, 7 a.m., 4:15.
It's noted as 5 KSI, 7 a.m., 4:15.
We use for leak checks, that won't suffice. I want a full new one.
We have 0, 100, and 5K right now.
They're in the bunkers, or they're in the Connex. We need the wheelie doodad, and it needs to be brought over to the little Connex, and then we need to wheel that over. If you could work on depressing the bottles and getting the new bottle ready to swap in.
Christopher and I are getting the new 6K.
Towards the Kwanzaa hut, right?
Take a right when you hit the Kwanzaa hut doors. LOX, breathe.
Box is disarmed, by the way. B?
Does it have a label on it, which one we're using?
The double doers, the two doers, and they say ERU 6KSI 4:15 7 a.m.
Copy, thank you. is coming out.
Locks breathe. Can we work on getting the other one at least staged if it doesn't make it all the way out before the time we clear?
Yeah, is someone working on getting another 6K?
Yeah, I got it.
Box breathe.
Are there 6K staged right now?
I think y'all got the only dolly.
Okay, Charles, we are ready to pressure panel ISO when you are.
Alright. Give me just a second. Red team. Could you read the bottle pressure off to me?
6100 PSI.
Alright, GHE tower ISO is going to de-energize, and then I need the ISO valve open. GHE tower ISO is de-energized. Good.
The pressure is up to 5K PSI on the load.
Arm DAC box.
Dalton, plug the pi enable key in.
It's too late, I can't access it unless you want me to take the panel off.
Alright, go ahead and take it off. Yeah, we're sitting pretty safe, guys, if you guys want to, like, stop being mega frantic.
Okay, understood.
Charles, we are closing ISO so that we don't lose a bunch of pressure through mains.
Sorry, main? Oh, yeah, go for it.
I remembered the pi enable when we got into the bunkers last time.
Save your breath.
eye is turned on.
Hey, red team, could you put that window back on, and then we're gonna arm the igniter and retreat.
Good pie over here. We have 15 minutes. Sorry, I'm stupid. 15 minutes off Charles's key.
Can I close the repress circuit? We're overpressing on the doer.
Yeah, close it, and then we're gonna reopen it. Unless you guys are good to retreat, I'm gonna restart locks load here.
Okay, yeah, we're about to retreat, so I'll leave it open.
Alright, do I have, did you press panel, the ISO?
Can you repeat that call out, please?
You make sure the press panel ISO is open and I have access to the bottle.
ISO is verified open and window is verified back on with PI enable key in.
Alright, restarting locks load, going for locks top off, red team DAC box arm. Prepare to all retreat, one DAC box open.
Dustin, turn around, get that guy, actually no, Dalton's out there, never mind.
DAC box is armed.
Verify safe. Flight control, all switches and keys off and safe.
We're in flight configuration.
Aborts, verify armed.
Ejector chill.
DAC, verified, or aborts verified arm, recover lead, go, no go. Flight control, GHG reg enable on. Flight control, QD arm, QD arms, arm. Flight control, QDs disconnect.
Main disconnect.
Flight control, GHG, QD, disarm when ready. Arm when ready. range. Go, no go. Flight control, firing sequence arm. Flight control, firing sequence on and perform test when ready.
said that the ignition leads are disconnected and that the recirc is closed.
Yeah, bottle pressure and dewar pressure, please.
Dewar pressure is 230 psi and bottle pressure is 0.
The dewar fill level.
This one doesn't have a nice gauge, but I'd imagine about half to 3/4 full.
Awesome. No new locks dewar needed. Could we stage the new 6K out there, please? And get and then we need the locks. If you can try to get the locks QD on, I would appreciate that.
The LOX QD's got some pressure behind it. I can't put it on.
Can I 45 the Locksman load?
Sorry, could you repeat that?
Can I go 45 degrees on Locksman load?
Yeah.
So you know, we closed off dewar and about to put on QD.
Great. Let me know when we can get the QD on.
Alright, hi everyone, we're back. Just want to give you all an update on what's been going on. So we attempted to launch, and due to a procedural issue, they failed to vent the GHE pressure line, causing the GHE quick disconnect to fail. They are going to reapproach, and they're not going to go horizontal, they're going to stay vertical. They need to reconnect their lines and go again for another launch attempt today within another 30 to 45 minutes. So we'll stay tuned. I may be coming back to answer some questions, but for right now, we're just going to sit back and let the launch team do their thing, and we'll let you know what's going on. Thank you.
Well, good thing we didn't launch. Wait, no, it's the B side is the one that controls, so. Yep, okay. Go ahead and give me a third barb on that one. Was dead.
Yeah, the bottle was reading 0 when I got out here.
Copy.
Hey Charles, we've got Locks QD on.
Great, closing locks fan. I am going to regulate pressure with the dump system. If you guys could clear out of the way, I'm going to just make sure I can use the dump system.
You don't have pneumatics.
You're right. Okay. Locks QD's on. I'm going to regulate pressure with the manual dump circuit, so I'll just keep you guys posted. Red team, work on getting pneumatics back up with an old bottle. Don't tap into a new bottle for pneumatics yet.
Copy.
Alright, red team, could you give me a status of the pad, please? Do you copy?
Sorry, can you repeat last?
Can I get a status of the pad?
Okay, so there is no pressure in the pneumatics. We are working on getting an old 6K connected. We can't quite remember how much pressure it had, but it was the newest one that we took off right before we put on the new 6K. Locks QD is on. We have the cherry picker coming over. He's going to lift our guys up. They're going to take wrenches. They're going to tighten the GHE quick disconnect. And then we are still loaded with fuel.
Alright, sounds good.
Do you need me to do any venting on the locks?
No, I'm gonna control with the solenoid.
Okay, good. Let me know if you need any more venting power through the dump line. backed off on vehicle load reg. Okay, I have the old 6K connected. It is sitting at 3500 PSI. I'm getting ready to connect, or getting ready to plumb muscle man rig with 120 PSI.
Fox breathe is connected.
Copy, thank you.
Charles, I need actuation on GHEQD.
I don't have muscle pressure right now.
Muscle pressure is set to 120 PSI.
Alright, going for GHEQD. Prop flow. Disconnects our arm. GHEQD.
And deactivate. One more time.
Missed that call.
And deactivate. You're on, thank you.
Tighten the fitting stack, so Dawson's going to tell you here in a second when to disconnect the GHEQD.
Copy, just let me know.
Charles, I'm not feeling any looseness in this fitting stack. Are you sure this is leaking?
Ben says the leak went away when we depressed the GHEQD.
Sure it's not a reg leak? Fitting stack up top is pretty tight already, so.
Alright, that's all we can do. It's operationally fine, so as long as you guys get those QDs on, I'll make it work.
We already did the fitting stack on the
issue. We have 3,500, 3500 PSI, and the current 6K that we have connected 120 PSI in the Muscle Man rig and nothing in the vehicle.
Alright, so Red Team, could you go ahead and give me that new 6K, but do not open the ISO valve yet, please?
Okay, so close ISO, vent, change 6Ks.
Correct.
Charles, just to confirm, we have new 6K plumbed up. I'm good to open up until ISO, correct?
No, keep that closed.
Keep the bottle closed?
Yeah, we're still making decisions here, so I don't want to waste any in the panel just yet. Okay, we're gonna sit here, pause for a little bit, and think.
Red Team, could you report the door pressure to me, please? Fill level again. It should be 3/4 at 230 PSI. Sorry, I think we talked over each other. And it's 3/4 full, right?
Yeah, it's somewhere between half and 3/4, I think. But the pressure is 210 PSI.
Red Team, can you... We're gonna get ready to recycle here. So... let's think what we need to happen. Hang on, Tom's got words. Alright, okay, Red Team, so we're gonna go, again, report the bottle pressure to me?
Haven't opened the bottle yet.
Alright, I want gas all the way up to the ISO valve, and then nothing past the ISO, please.
Or past 6100 PSI.
Great, okay. Red team, we're going to restart procedures at LOX, gas load prep.
Red team, muscle regs, verify set at 120 PSI.
Am I ready to open the panel ISO?
Yeah, we're gonna restart procedures here, so go ahead and go for panel ISO.
Pressure set to 120 PSI.
Red team, LOX tower, man ISO, verify closed.
LOX for man ISO is verified closed.
Red team, LOX load is set to fill.
LOX man load is set to fill.
Red team, cryo gloves, put on.
Guys, if we need to remote cameras, now is the time to start thinking about that.
Kyle, do you need to come back out here, or are you good from last time?
He's good.
Cryo gloves are donned.
Red team, LOX tower, verify put in position, clear of debris, and connected to the LOX panel.
Verified. Put in position. Connected to LOX panel and clear debris.
LOX tower, report pressure.
LOX tower sitting at 210 PSI.
Red team, LOX tower, open. Full open on LOX tower. And can we crack that repress open halfway?
Don't do the repress yet.
Copy.
We are full open, quarter turn back on LOX doer. No repress.
Copy, thank you.
Red team, cryo gloves, take off.
Cryo gloves are off.
Red team, DAC box, verified disarmed.
DAC box verified disarmed.
Copy. We're gonna get the FAR guys to let people know we're going for another attempt.
Is the DAC box disarmed?
Yeah, I said that DAC box verified disarmed. Sorry, I must have.
All, prepare to retreat. Red team, remote cameras, start recording.
Do we want to put in the pie yet? Did you get my last?
Yeah, I did get your last. Hang on, we're discussing. Pi disconnected.
Okay, pie is disconnected. Remote cameras are in there. The state we want them to be in.
Red team, ignition leads, verify connected, and igniter assembled correctly.
Ignition leads are not connected. Do you want me to do that right now?
Connect the ignition leads to the engine.
Igniter is assembled correctly and ignition leads are connected.
Copy.
Alright, I'm going to start lock load sequence, and then we are going to arm DAC box and set the load reg. Any questions or concerns or comments about that sequence of events?
Do we connect the pie at all?
No, we are going to fly with it disconnected.
Okay, sorry, I misinterpreted that call then.
No worries.
Alrighty, I think I'm good with that order of events. Then we are putting the panel on and you can proceed with LOX load.
Alright, sounds good. Venting tanks down to start LOX load. Alright, beginning LOX load. Could you give me a repress circuit, please?
Fully open?
Yeah, give me a full open, please. And then, red team, could you go ahead and we need the DAC box arm, please.
You said DAC box arm, correct?
Correct, DAC box arm.
Press circuit is fully open, quarter turn back.
Alright, red team, load reg set at 500 PSI, or 5,000 PSI.
DAC box is arm, can you verify igsense?
somewhere between half and 2/3 full.
We are set at 5000 PSI.
Sweet. Alright. Red team, do one final pad sweep. Let me know if you find anything, see something, say something, and we are going to get you guys out of there. So, red team, one final pad check, then retreat.
That sweep looks good. We're retreating.
Hey, can you tell those guys that we are in the middle of LOX load and don't get committed to whatever they're doing?
Told them.
Hey, red team, could one of you guys shadow the far guy that's running out? Just want to make sure that we have comms with him. Alright, moving to test.
Flight control, all switches and keys off and safe once LOX load is complete. DAC, abort, verify armed.
Injector chill.
Data. Aborting, looks like main valve froze.
we're standing down. Alright, Red Team, could you guys approach, disarm the DAC box, and disconnect the igniter leads, please? Just be careful that we are still boiling off some locks through the mains that I can't control, so if you guys can't get to the igniter leads safely, don't do it. Close the doer, close the bottle, and disarm the DAC box, please. Let me know when you have the gas bottle closed, the doer closed, and the DAC box disarmed.
Doer is closed, bottle is closed, DAC box is disarmed.
Copy. Red Team, if you want to... Ooh, hang on.
Igniter leads are disconnected.
Alright, great. So, can we attach the fuel QD, and then I want the fuel drained into the fuel bucket, please. You can go through the manual path. Go through the manual path, and then we're going to take all the muscle pressure out of the system. So, if you guys want to depress the gas system, and drain fuel afterward.